My name is Yuya Matsumoto from NEC Corporation. Today, I'm introducing a novel approach to utilize line correspondences as well as point rounds for individual localization. Visual localization is one of the important computer vision applications. Its aim is to estimate the 6 DOF camera pose of input query RGB image for given 3D model. 3D model is often constructed by SFM or LiDAR. Also, a lot of database images are given. They are localized images which capture somewhere in the 3D model, and each pixel of the image is associated with corresponding 3D point. The input is an RGB image as a query. And what we want to estimate is the 6 DOF camera pose of the query image for the 3D model. The mainstream of visual localization is coarse-to-fine-based approach. This approach begins by image retrieval in core step. In this step, top-K database images that are similar to input query are quickly obtained by calculating the similarity of global descriptors. In fine step, point feature matching is conducted between query and the top-K database images to get 2D correspondences. By using 3D information of database images, we can convert these 2D correspondences to 2D ones. Finally, PnP uses these correspondences to estimate 6 DOF camera pose of the query image. This coarse-to-fine approach is very simple and strong. The performance of this approach depends on how many and how accurate point correspondences are obtained. However, the point-based approach often fails in indoor environment due to its several difficulties. First, indoor environment is textureless compared with outdoor. It is very hard to detect sufficient key points in textureless scene. Also, even if key points are detected, point correspondences are sometimes concentrated to local area. These concentrated correspondences lead to unstable camera pose estimation. And there are a lot of repetitive patterns due to artificial environment. These repetitive patterns cause false point correspondences. Therefore, conventional point-based approach doesn't work well on indoor environment. On the other hand, many lines are detected even in textureless scenes in indoor environment. This motivated us to propose a novel pipeline to utilize line correspondences as well as point ones. Our pipeline starts by image retrieval as usual. After that, it conducts camera pose estimation using lines twice. These two estimation modules play different roles. The first pose estimation makes localization robust to repetitive patterns by using lines. In the second estimation, prospective endpoint and line utilizes both point and line correspondences to realize stable camera pose estimation. Also, these two modules employ different methods to get line correspondences. The first module finds line correspondences by geometric approach and the second module by line feature matching. First, I will explain about the first estimation module. In this module, point correspondences are obtained by feature point matching between the query and database image. Also, lines are detected. Please note that the lines are not matched since the query and database image often have large viewpoint gap and existing line feature matching often doesn't work in that case. Line correspondences are obtained during the following RANSAC process. In a RANSAC loop, P3P is conducted by using 3 point correspondences to calculate temporal camera pose. Then by using the temporal camera pose, point inliers and line inliers are calculated. In line inliers calculation, we consider lines detected in the query and database image. We can obtain 3-dimensional coordinates of lines that are detected in database image by using its 3D information. Then the temporal camera pose projects these 3D points to the query image. And calculate angles and distance between the projected endpoints and all the query lines. If the line pair satisfies angle and distance threshold and mutual nearest neighbor condition, it is regarded as an inlier pair. Then we compute RANSAC score by point and line inliers following this equation. By considering line inliers to calculate RANSAC score, we can prevent RANSAC score from getting higher by false point correspondences due to repetitive patterns. Finally, PnP uses point inliers to estimate the camera pose. Next is localization step. This step refines camera poses by re-estimation. In this step, we use camera poses estimated by the previous step to generate rendered images. First, point and line feature matching are conducted between the query and the rendered image. In this step, existing line feature matching works well since viewpoint gap between the query and the rendered image is small, if camera pose is correctly estimated in the previous step. Then RANSAC starts and the point and line in layers are determined. Please note that we don't make a comparison between all the lines of the query and database image since we have line correspondences. Then calculate RANSAC score. And both point and line correspondences are used to estimate camera poses by perspective and point and line, PmPnL. PmPnL simultaneously minimizes point reprojection error and line reprojection error between two projected endpoints of database line and the corresponding query line. Lines are detected even in textualess scene, therefore point and line correspondences are complementarily obtained, and these spatially distributed correspondences stabilize camera pose estimation. Finally, this pipeline outputs an estimated camera pose. In our experiments, we compared our proposal with another pipeline using only points as baseline. We evaluated our approach by a large-scale window dataset InLoc. This dataset includes 356 query images and about 10,000 database images. Query images are taken only on 2 of the 5 floors, DUC1 and DUC2. The scores are measured as the accuracy of estimated camera poses, whose angular error is within 10 degrees and whose positional errors with 3 threshold values, 0.25 meter, 0.5 meter, and 1 meter. The experimental result is here. Blue represents the performance of existing approaches, and orange represents the baseline using points and our proposal. As it can be seen, our proposal achieved state-of-the-art for 4 out of 6 scores. Also, compared with baseline using points, the usage of lines improves all the scores. These results show that our pipeline effectively utilizes line correspondences to realize high localization performance. Next, we show an example to explain that how line correspondences improve localization. The left figure shows point matching for the database image with the highest inlier score. As you can see, this point correspondence is wrong due to the repetitive patterns of the carpet, which leads to the wrong camera pose. On the other hand, the right figure shows point and line in layers when using our pipeline. This matching is accurate, as you can see. Even if repetitive patterns increase false point in layers during RANSAC loop, line in layers become small since point and line in layers are not consistent in that case. As a result, false point in layers does not increase overall RANSAC score, and only when point and line are consistent, the score gets high. In this way, our pipeline makes localization robust to repetitive patterns. Here's another example to show the line impact. These figures show query images with the edges detected from rendered image generated by estimated camera poses. In the left figure, you can find the estimated camera pose by point-based approach is not aligned the area near to the camera. It's because point in layers are concentrated in textureful area that is far from the camera. On the other hand, the result of our pipeline, which is shown in the right figure, is aligned to the area near to the camera. This is because line correspondences are also detected in textureless objects, and PmPnL uses these spatially distributed correspondences of points and lines to realize stable camera pose estimation. Finally, we present a conclusion. First, we proposed an approach to effectively utilize point and line correspondences. Also, the first estimation module makes localization robust to repetitive patterns, and second one utilizes point and line correspondences to realize stable camera pose estimation. And our pipeline achieves state-of-the-art scores for large-scale indoor dataset. That's all. Thank you for your listening.